In this next unit, we discuss our final application of integration we're going to discuss in this class. And this is an application to something called moments, centers of mass, and centroids. Here is the basic question. Given a thick plate of uniform density and any shape, how could we find the point P on which this thin shape will balance horizontally? So we have some weird, goofy shaped thing. We want to figure out where is that point which you could place a fulcrum so that it would balance. And one thing we do assume here is that the plate has uniform density. If you don't assume that, it gets a little bit more complicated. Now, the first thing we're going to consider is the one-dimensional case. Now, the one-dimensional case is like a seesaw. So what we have, we're going to consider a rod with two masses. So consider a rod with two masses, M1, M2. Attached to a rod with negligible mass. At distances D1, D2 from a fulcrum or a center point. So this really is like a seesaw. You have mass 1 over here. Somewhere over there you have mass 2. And somewhere in the middle is your fulcrum, or well, somewhere in between them is your fulcrum. This is distance 1, this is distance 2. Now from physics, the law of the lever says that this will balance if M1 times D1 equals M2 times D2. And you can think that this shouldn't make sense because if mass 1 is greater and you were on a seesaw, you'd have to sit closer to the center to balance out with the other lighter person. So now what we're going to do is translate this into points lying on the x-axis. So we're going to suppose our rod lies on the x-axis. So suppose our rod lies on the x-axis. And we're going to call that fulcrum point be the center of mass, and we're going to give it a name. We're going to call it x bar. So let x bar equal the center of mass. Okay, and just for simplicity, we're going to assume that those points are bigger than 0, but this would work if they were not as well. So here's 0, here's the point x1, here's the point x2. At x1 we have m1, and at x2 we have m2, and x bar is somewhere in between them. We're not sure exactly where. Now what we're going to need are expressions for this distance and this distance. And once we have them, we can use this law of the lever to solve for x bar. So notice that the first red line, that distance will be given by x bar minus x1, because x bar is greater than x1. The second one will be x2 minus x bar. Now from the law of the lever, we know that to balance, we have to have m1 times x bar minus x1 equals m2 times x2 minus x bar. So what we're going to do now is solve this for x bar. Distribute x bar m1 minus m1 x1 equals m2 x2 minus x bar m2. Now put the x bars all on the same side. X bar m1 plus x bar m2 equals m1x1 plus m2x2, and factor out the x bar. And divide by m1 plus m2. All right, and that tells us, just using the x coordinates, the location of those masses and the masses themselves, that tells us the location of the center of mass on the x-axis. Now this numerator is referred to as the sum of the moments. The denominator is the sum of the masses. All right, let's do an example. Suppose you have a 20-pound child and a 60-pound child, and they sit on a seesaw that's 5 feet long. Where do you need the fulcrum to be so that the beam is going to balance? So suppose our 60-pound kid is over here, Mr. Big Head, and over here is its little brother, and that kid is just 20 pounds. And let's call the distance from the 60-pound kid to the fulcrum, let's call that x. Since the seesaw is 5 feet long, this distance, the little kid, has to be 5 minus x. And using the law of the lever, you know that 60x has to equal 20 times 5 minus x, or 60x equals 100 minus 20x. 80x will equal 100, and so x will equal 100 over 80, which is 10/8 or 5/4, or 1.25 feet. And you got to be a little bit specific about how you specify 1.25 feet. How? Is it 1.25 feet from the small kid or 1.25 feet from the big kid? In this particular example, the way that I constructed the picture, it's 1.25 feet from the 60-pound child. Now suppose we have 3 things and they're on the x-axis. So the formula we found in a couple of slides ago generalizes. You just sum the moments, which are given by mi times xi, and then divide by the sum of the masses. So let's plot these points on a number line. At -5, we have m1, and that has a mass of 7. At 1, we have m2, and that has a mass of 3. And then at 3, we have m3, which has a mass of 5. Now to find x bar, we add up the sum of the moments, which are given by m1x1, m2x2, m3x3, all over m1 plus m2 plus m3. So mass 1 is 7, its x-coordinate is -5. Mass 2 is 3, its x-coordinate is 1. 5, x-coordinate of 3, all divided by 7 plus 3 plus 5. So in the numerator we have -35 plus 3 plus 15, all over 15. So that's -17 over 15. Now suppose we generalize to a 2-dimensional case. We have points floating on a plane. So here's the general picture. So we have some mass m1, that's over a distance of x1 and up a distance of y1. Some mass m2, that's over a distance of x2 and down a distance of y2. And some mass m3 over here, that's back a distance of x3 and say up a distance of y3. And the question is, how would you find the balancing sort of center point of this? I'm a total Doctor Who nerd, so this makes me think about the episode with the planets and finding where they balanced and the Daleks in the machine. If you don't like Doctor Who, that's okay. So what you do is you do this one dimension at a time. So first, you find what's called the moment about the y-axis. Now, what that means is you kind of squish this picture down and only look at the x-coordinates. And you sort of balance it that way. The reason it's called the moment about the y-axis is because those masses would be kind of rotating left or right over that y-axis. But what you're going to look at is, what would be the moment if I only had x? And that's the moment about the y-axis. Now you're going to, and then for the other one, you look the other direction. Moment about the x-axis is how those dots are going to rotate up, back and forth. And for that, you're just going to look at and find the middle y. So find the middle x and the middle y, and that will be your middle point. So here is the notation. So you have moment about the y-axis. So my will be the sum from I equals 1 to n of mi xi. So like m1 x1 plus m2 x2, etc., all the way up to mn xn, your last one, whatever one that is. And this part can be tricky just because you look at the x's to see how this picture flips over the y. So my, the formula involves x's. Now the moment about the x-axis mx will be a sum from I equals 1 to n mi times the y coordinates. So m1 y1 plus m2 y2 all the way up to mn yn. And the total mass of the system will be m1 plus m2 plus the last one. And so x bar is going to be given by my over m, which you can think about as a sum of mi xi over a sum of mi. That might be easier. Finding x bar involves x's. Y bar is the moment about the x-axis over m, which is a sum of mi yi over the total mass, sum of mi's. And finding y bar uses y's. It might be useful to think about it that way. All right, so let's apply that to find the center of mass of this given system. So x bar will equal my over m, or a sum of mi xi over all the masses added together. So let's just up here compute that m, or the sum of all the masses, is 12 plus 6 plus 4.5 plus 15, or 37.5. And then to find mi times xi, I just take the mass multiplied by the x-coordinate at that point. So 12 times 2 plus 6 times -1 plus 4.5 times 6 plus 15 times 2 all over 37.5. And that gives us 75 over 37.5, or 2. So x bar is 2. And then y bar is mx over m, which is the sum of mi over m, which we already found to be 37.5. So the miyi will be 12 times 3, 6 times 5, 4.5 times 8, and 15 times negative 2, all over 37.5. So that's 72 over 37.5. And it's kind of bad form to leave fractions over fractions. So since it's just 0.5, you can compensate by multiplying that by 2 and that by 2, and you no longer have a decimal inside of a fraction, which is just bad math grammar. So this is 144 over 75. And this probably does reduce because it turns out that 3 goes into 144. And the way that you can tell that that's true is 1 plus 4 plus 4 is 9, and 3 goes into 9. That's a sum the digits up, and if 3 goes into the result, 3 goes in the original number. So that's 48 over 75 divided by 3 is 25. And now that doesn't reduce anymore. Now we're going to actually generalize this two-dimensional idea to finding the center of mass given a weird shape of uniform density. So you have a region R of uniform density, rho, which lies between two curves f of x and g of x, where we're assuming that f of x is greater than g of x. Then these are the equations for the moments, and the centers of mass are given by dividing the moments by the total mass, and the total mass is rho times the integral from a to b of f of x minus g of x. Notice that f of x minus g of x is actually the area of the curve. And in the positive sense, because we assumed f of x is bigger than g of s. So that's like area, real area, not area signed. So let's figure out where the formulas come from. Okay, so first let's start by drawing the picture. Or a picture, there isn't only one. We have some curve f of x and some curve g of x between some a and some b. So it has a weird, funky shape. This one isn't so funky, but we'll pretend it's a little bit more funky. And we want to find the center of mass of this shape. So like many things, we take this thing and we cut it into little chunks. And here's how we're going to use that chunk. So first thing is we need both of those formulas for centers of mass involve finding the total mass. So we assume the density is uniform. So the density is represented by the Greek letter rho. Okay, and we have that the mass is equal to the density times the area. So that's rho times the integral from a to b. The area between those curves is given by f of x minus g of x dx. And just to make it easier, I'm going to call that a. So rho times a. All right. Now we need to find the my and the mx. Okay, so we divide this up into little pieces where delta x is equal to b minus a over n. And in these little rectangles, I'm going to let x sub I be the center of the ith subinterval. So x sub 1 is the center of the first subinterval. X sub 2 is the center of the second rectangle. Now remember that my formula for my was this sum from I equals 1 to n of mi xi. So mass times location. So if I wanted to balance this thing along the x-axis and solve for rotation about the y-axis, I've got to find the balancing point this way, which is found by taking the mass times the x-coordinate of a slice. Now the mass of a slice, my slices are rectangles, density rho times the area, well, the height of the rectangle is f of x sub I minus g of x sub I, and the width of it is delta x. So that's every rectangle's mass, and then x sub I is how far over that is. So we have a sum from I equals 1 to n of rho f of x sub I minus g of x sub I delta x. And I should probably say that my actually approximately equals that, because if we haven't taken the limit, we don't have it exactly. But once we take a limit, we get this my exactly, and my will equal an integral from a to b rho times x times f of x minus g of x dx. And that finds the center x value, which tells you, if you were to say take a flat sheet and move that sheet over where you'd place it. So a flat vertical sheet, and you kind of slid it across until you balanced along that sheet, well then that's the place you're looking for. And from that, we know that x bar is my over m. And here's the interesting thing, those rows don't matter. My over m is going to be rho times the integral from a to b of x times f of x minus g of x dx over the total m, which is rho times a. So what I'd like you to know for x bar, that's calculated using 1 over a integral a to b x times f of x minus g of x. So that's the formula for x bar. The fact that the uniform density is rho just drops out of the equation when you do that division. So that's the middle x part. Now we do the same thing. We want to find rotation about the y, so we think about taking a horizontal plate and like moving it up and looking for where would we have that balancing point. So to find that, we find the moment about the x-axis, and that's given by a sum from I equals 1 to n of mi yi. Now we found in the previous part that mi was equal to rho times f of x sub I minus g of x sub I delta x. That's the mass of a slice. Now to find the middle y sub I. To find the center y sub I, you find the average of those two values, and that would give you the center point of each piece. So we have that y sub I will equal 1/2 f of x sub I plus g of x sub I. And plugging that in, we have that mx is about equal to the sum from I equals 1 to n rho f of x sub I minus g of x sub I times 1/2 f of x sub I plus g of x sub I delta x. And to get it exactly, we take a limit. We have rho, which becomes an integral from a to b. We have this 1/2. And notice when you multiply this with this, you actually have f of x squared minus g of x squared. And then once again, to find y bar, you take mx over m. And in doing so, your rows will cancel. You'll have 1 over a. You just have that extra 1/2. So 1/2, 1 over a, integral from a to b, f of x squared minus g of x, quantity squared, dx. These problems get a little long because you have quite a few things that you have to integrate, but in general, I would say start by finding the area, because that's needed for both formulas, and then using that find x bar, y bar. So let's do a few examples. So in summary, here are the formulas that you should use to find x bar and y bar. So I would always suggest first to find a, find the area between the curves, a to b, f of x minus g of x dx. And of course, it's assuming you have actually graphed the curves first. So we're going to find mx, my, and x bar, y bar for this lamina of uniform density row bounded by the graphs of these equations. We're going to actually skip the mx, my part, and we're just going to go straight to the x bar, y bar. So step 1, find the area, and that's after step 0, which is to graph the curve. So e to the 2x is an exponential increasing function. When you plug in 0, you get out 1, and it looks something like this. Y equals 0 is the x-axis, x equals 0 is the y-axis, and x equals 1. So there's the region we're talking about. So the area is given by an integral from 0 to 1, e to the 2x dx. The antiderivative of e to the 2x is 1/2 e to the 2x, calculated from 0 to 1. So 1/2 e squared minus 1, or e squared minus 1 over 2. So that's the area of the curve. Now after you have that, let's find x bar. So x bar is equal to 1 over a, integral a to b, x times f of x minus g of x. Now in this case, my second curve, g of x, is actually 0, and my f of x curve is e to the 2x. Now notice when you do 1 over a, you'll have 1 over the quantity e squared minus 1 over 2, which means that e squared minus 1 over 2 reciprocates and becomes 2 over e squared minus 1. Integral 0 to 1, x e to the 2x dx. And at this stage, you have to remember how to integrate x e to the 2x. This is not a substitution problem. This is actually integration by parts. So we let u equal x, du is dx, dv is e to the 2x dx, and v is 1/2 e to the 2x. All right, so moving up where I have some space, we'll have 2 over e squared minus 1 multiplied by the quantity uv, so 1/2 x e to the 2x. That part no longer has an integral, so it needs to be evaluated from 0 to 1, minus v du, so this was uv minus integral v du. So minus 1/2 integral v du will be 1/2 e to the 2x dx. Don't forget your bounds, 0 to 1. All right, now continuing and plugging some stuff in, we'll have 2 over e squared minus 1 times 1/2 e to the 2, and plugging in 0 just gives us 0. When we antidifferentiate the e to the 2x, we get 1/2 times 1/2, which makes 1/4. e to the 2x, evaluated from 0 to 1. If you're going to make a mistake, it's probably right here. There are some potential sign errors that are happening. 1/2 e squared minus 1/4 times e to the second minus 1. So notice that negative will distribute to the 1. We have 2 over e squared minus 1 times 1/2 e squared minus 1/4 e squared plus 1/4. And 1/2 of an e squared minus 1/4 e squared is 1/4 e squared. So you have 2 over e squared minus 1 times 1/4 e squared plus 1/4. I know, I'm so sorry. 2 over e squared minus 1 times e squared plus 1 over 4. And finally, after much pain, you have e squared plus 1 over 2 times e squared minus 1. Whatever that is, it's x bar. And now that you've thoroughly exhausted your integration, you have to now find y bar. But it turns out y bar is actually quite a bit easier for this problem. So remember, the equation for y bar is 1/2 times 1 over a, integral a to b, f of x, the quantity squared, minus g of x, the quantity squared, dx. And once again, my g of x curve is 0. So we'll have 1/2 times 2 over e squared minus 1, integral 0 to 1 e to the 2x, that's squared, dx. Those 2's cancel. And you have to remember your rules for exponents. E to the 2x squared, those exponents multiply and you get e to the 4x. So when we anti-differentiate, e to the 4x, you get 1/4 e to the 4x. So 1 over 4 times e squared minus 1 multiplied by e to the 4th minus 1. And you're almost done. It's just that this expression actually simplifies. E to the 4th minus 1 factors into e squared plus 1 times e squared minus 1. And notice how those e squared minus 1's cancel. And so your final answer for y bar is e squared plus 1 over 4. So another example, find mx, my, and x bar, y bar for this lamina of uniform density rho bounded by the graphs of sine and cosine. So in the previous example, we had an example of integration by parts. We're probably going to use some trig stuff here, and also actually integration by parts. All right, so first, sine and cosine. It is unacceptable that you are in calculus 2 and you can't graph sine and cosine. You need to figure them out if you don't know them. Okay, and rant. So sine begins at 0. By pi halves, it's up at 1. By pi, we're back down at 0. So there's part of a sine curve. Cosine begins at 1. By pi halves, we're at 0, and by pi, it's at -1. So, ish, there's your curves. You gotta find this intersection point. I'm assuming we mean just the center of that part. So notice that we need to figure out where does sine equal cosine. So you think about, and also before pi halves, so the angle that makes that happen is pi quarters. So step 1, find the area. So we have the integral from 0 to pi quarters. For that portion, the cosine curve is above, the sine curve is below. Now the antiderivative of cosine is positive sine. The antiderivative of sine is negative cosine, but the double negative makes it positive cosine. And plug in everything in, we get root 2 over 2 plus root 2 over 2 minus sine of 0 is 0, cosine of 0 is 1. Root 2 over 2 plus root 2 over 2 is root 2 minus 1. So there's the area. Now to find x bar, we do 1 over a integral a to b x times f of x minus g of x. So that's 1 over root 2 minus 1 integral 0 to pi quarters x times cosine x minus sine x. And I understand that it might be your first instinct to distribute here. I would actually suggest not doing that because you can do integration by parts with this as it is right now. Let me show you what I mean. Let u equal x, du will equal dx. Let dv be the entire cosine x minus sine x dx part. Anti-differentiate that, and for v, we get sine x plus cosine x. Okay, remember that the integration by parts formula is uv minus integral v du. Okay, great. So now plugging that stuff in, so we have that 1 over root 2 minus 1 out in front, uv, so x times sine x plus cosine x, that's evaluated from 0 to pi fourths, minus v du, so minus the integral from 0 to pi fourths of sine x plus cosine x. So sine x plus cosine x. And notice that that latter integral is one that you can actually handle, so it's not so bad. So we have 1 over root 2 minus 1. Now plugging stuff in, we'll have pi quarters times root 2 over 2 plus root 2 over 2. Plugging in 0 will yield 0 because of the x coefficient. Minus, now let's anti-differentiate. Sine's antiderivative is negative cosine. Cosine's antiderivative is sine. From 0 to pi quarters. Be careful with your signs. So this becomes 1 over root 2 minus 1 times pi root 2 over 4. The root 2 over 2 plus root 2 over 2 just became singular root 2. Okay, now plugging in pi quarters, we're going to have minus, brackets there. So negative root 2 over 2 plus root 2 over 2. Minus, plugging in 0, negative 1 plus 0. Okay, so here we have 1 over root 2 minus 1 times pi root 2 over 4. These canceled. And we have 3 negatives, making that a minus 1. If you feel like it, you can get a common denominator and write this as pi root 2 minus 4 over 4 times the quantity root 2 minus 1. Nobody promised that your centroid would be in a pretty spot, and this one's in a particularly ugly spot. So there's the x bar. Now, y bar actually, like the last one, isn't quite as bad. So recall the formula for y bar is 1 over 2 times 1 over a, integral from a to b, f of x squared minus g of x squared dx. So 1/2 times 1 over root 2 minus 1, integral from 0 to pi quarters, and we have cosine squared x minus sine squared x. And I know you thought you were done with trig forever, but what you're going to have to do here is use those fancy half-angle identities. So cosine squared and sine squared. Thankfully, some nice stuff will cancel. 1 over 2 times root 2 minus 1. Now recall from the half-angle stuff that cosine squared is 1/2 times 1 plus cosine of 2x. And sine squared is 1/2 1 minus cosine of 2x. Everybody has the greatest common factor of 1/2, so I'm going to factor that out, which makes this 1 over 4 times root 2 minus 1. And when that 1/2 is gone, notice how I'm going to have 1 minus 1, and those 1's cancel. And I have this cosine 2x minus this negative cosine 2x, making 2 cosines of 2x. And that 2 can cancel with the 4 in the denominator, making this into 1 over 2 times the quantity root 2 minus 1. And we still have to integrate our cosine function, but that's not super hard. 1/2, so we're back to a quarter. 1/4 root 2 minus 1. Cosine's antiderivative is sine. Note I compensated for the 2 by making that into a 4. So we have 1 over 4 times root 2 minus 1 times sine of pi over 2 minus sine of 0. And you should know that sine of pi over 2 is 1. So we finally have that y bar is 1 over 4 times root 2 minus 1. Whew! Those problems take a long time, and as such there will not be very many of them, but I thought it was a really good chance to review certain special integration techniques. Now, the last thing we're going to discuss is this interesting theorem called the Theorem of Pappus. So this lets us use centroids to find the volumes of regions. It turns out that this is actually quite related to cylindrical shells. So here it is. We have some region R bounded by 2 curves. Let's call them f of x. Let's call the second one g of x. And we'll say it's between some a and some b. And let's say we're going to spin this around the y-axis. So if we were to use cylindrical shells to find the volume of this, the volume will be 2 pi integral a to b. Your radius out to a slice is x. Your height of a slice is f of x minus g of x. And that expression should look awfully familiar, like really familiar. And here is how you know this. You know that x bar is 1 over a integral a to b x times f of x minus g of x dx. And therefore that integral without the 1 over a is equal to a times x bar. So this tells you you can have 2 pi times the area times x bar. And this is particularly useful if the area of your region is easy to find. Like suppose you have a circle and you know it's a circle, and the centroid could also be very, very easy to find. So notice one thing is that this is for about the y-axis. And I would conjecture that if you rotate about the x-axis, it's going to be 2 pi a times y bar. But that actually isn't super obvious. Let's talk a little bit about why that's true. So if you were going to find the volume of that region when it's spun about the x-axis, I think it would probably be better to use the disk method. So the volume would be an integral from a to b pi r out, which would be f of x squared minus r in, which is g of x squared dx. And that's pretty darn similar to the formula for y bar. So remember that y bar is 1 over a, integral a to b, or 1 over 2a, excuse me, a to b, f of x quantity squared minus g of x quantity squared dx. And so thus 2a times y bar is the integral from a to b of f of x, the quantity squared, minus g of x, the quantity squared. And so you can plug in 2ay for that expression, and notice this pi actually has to hang out and stay. So you have pi times 2a y bar, or 2 pi a y bar. So, to find the volume, if you spin about the y-axis, you find the average x. To find the volume when you spin about the y-axis, you're going to find the average from middle y. So here's an example where using this theorem makes it very easy to find a volume. So suppose you rotate the circle x minus 2 squared plus y squared equals 1 about the y-axis. Circle of radius 1 moved centered at 2, 0. When you spin this about the y-axis, you get a donut. And the volume using the theorem of Pappus is 2 pi area times the x bar. And well, we have a circle, and the circle has radius 1, so its area is pi times 1 squared. And now x bar can be estimated visually. If you go along draw vertical slices along the x-axis, where's the middle going to be? Well, obviously it's right there at x equals 2. That's the middle point. You can use that symmetry principle to make other things also go more quickly. So this would equal 2, and the volume is 4 pi squared. Next, let's use the theorem of Pappus to find the volume formed by revolving the region y equals 2x, y equals 4, x equals 0 about the x-axis. Alrighty, so y equals 2x goes through the origin, 1, 2, 2, 4, y equals 4, horizontal line, x equals 0, y-axis, this is the region we're looking at. We're spinning about the x-axis. So the theorem of Pappus says the volume of this thing is 2 pi times the area times y bar, the average y, which should probably fall somewhere up there-ish. So first let's find the area. Well, we have a triangle. 1/2, base is 2, height is 4, so the area is 4. Now we need to find y bar. Well, that will be 1/2, 1 over a, integral from a to b, f of x squared minus g of x squared. And notice that f of x, the upper curve, is actually that constant y equals 4. So we have 1/2 times 1/4, integral 0 to 2. 4 squared, which is 16, minus 2x squared, which is 4x squared. I'm going to factor out a 4, which will cancel with that 1/4, giving me a half. Integral 0 to 2, 4 minus x squared dx. So 1/2 times 4x minus 1/3 x cubed. So that's a half times 8 minus 8/3, or 1/2 times 24/3 minus 8/3, which is 1/2 of 16/3, or 8/3. And using our theorem of Pappus, the volume is 2 pi times 4 times 8/3, or 64 pi over 3.